modulus argument and polar trigonometric form of complex numbers. We're going to break this down into two videos. The first is about the modulus and the argument, and the second is about polar trig form. This is exercise 16E. Okay, so a little starter question. If I gave you two complex numbers, z equals 2 minus I and w equals 1 plus 2i, how do you know which complex number is bigger? So you could think about it, well, maybe we'll compare the real and imaginary parts of the complex number. Maybe we can see which parts are negative or positive. But on its own right now, we don't have a really good way to figure out the size of a complex number. So this is what we're going to investigate. One way of measuring the size of a complex number is measuring the magnitude or the modulus, sometimes denoted by R or the absolute value of the complex number z. This simply represents how far away the complex number is from the origin. And note that this distance or this modulus is always going to be the positive distance. As we can see in the diagram, if I have my complex number z, that little red dot, then the modulus R is simply the distance of that dot from the origin. Now we can figure out what the modulus or R is using Pythagoras. We say that R squared equals the real part A squared plus the real part B squared, and of course we take the square root, the positive version, just to find R by itself. Let's have a look at some examples of finding the modulus of a complex number. B. Find the modulus of W. We're going to do the same thing, but W is 3 minus I. So the modulus of W, denoted by the absolute value of W, equals, take the square root, A squared plus B squared. Now, my real part or my A is 3, my imaginary part is minus 1. Do not include the I in this. There should never be an I in your modulus formula. And then we take the square root of these two parts added together. So we have the square root of 3 squared plus, in brackets, minus 1 all squared. This should be the square root of 10. Question C is just in there to help you use your calculator. If you are asked to use your calculator to find the modulus of z plus iw, okay, what you can do on a CAS calculator is go to your normal calculator settings, then go menu, number. From here, find complex tools. I think it's down the bottom. And there should be a button either called magnitude or modulus. Once you find that, you can just type in z plus iw, which is 7 plus I times 3 minus I. Press equals and it should spit out the modulus of this giant number. We're going to do it by hand. So z plus iw can really be written as 7 plus I times 3 minus I. And then I'm going to take the modulus of all of this. But first, simplify or expand whatever's inside as best you can. I times 3 minus I, let's do that first. You'll get 3I minus I squared. Okay, group your real and imaginary parts together. And remember that I squared is the same thing as negative 1. So we'll have 7 plus I plus 3I is just 4I, minus the I squared was just negative 1, so sub it in. Then take the real parts. 7 minus minus 1 is 8, plus the 4I that I had from my imaginary parts. Now we're ready to take the modulus of this number. So again, identify the real and imaginary part, or your A and B. The real part is 8, so we're going to square that. Then we're going to add on the imaginary part, that's 4, square that and take the square root, just like Pythagoras. And we'll get something like the square root of 80. And in the end, we'll get 4 root 5. Now there is another way to measure the size of a complex number, and that is in terms of the angle that your complex number makes with your real axis and with the positive real axis. This angle is called the argument. In general, we want our argument to be written between minus pi and pi. If we include this domain, it's called the principal argument, and this is what we're going to use all the time. So in our diagram, again, I can see my complex number z is a plus bi, and I'm trying to find this angle theta, okay, which is from the positive real axis all the way up to my complex number. So we can use simple trig because we will have formed a right angled triangle, and we're going to use tan. So we can say the argument of z by using tan, well, we know that tan theta equals opposite over adjacent, so B over A, or your imaginary part over your real part. And then, of course, you can either take the inverse of this to find theta if it's in an appropriate domain, or you can use your knowledge of the tan graph and identity triangles to help you. Let's have a look at some examples where we're asked to find the principal argument of the following three complex numbers. I'm just going to draw a table with the complex number, the graph of the complex number, and then my working out to find that argument. Now, I like to use the graph and just a little bit of trig to find out my principal argument. Just remember that the principal argument is always needs to be represented as between minus pi or minus 180 degrees and pi or 180 degrees. So if I have z1 equals minus 3i, the first thing I do is I draw a little graph of that. We have minus 3 on the real axis, and we also have conveniently minus 3 on the imaginary axis. So here's my dot or my complex number, z1. I'm just going to draw a little line in that will help me. So for my argument, I start at the positive real part of my axis, okay, the horizontal axis, and I have to make a choice. I can either have theta go around in the anti-clockwise direction, but if I do this, theta will be bigger than pi. This is outside my restricted domain of the principal argument. So instead, I have to go the other way around from the positive real axis underneath and clockwise around until I get to that line and until I get to my complex number. If I do this, notice that theta will be between minus pi and pi. Because minus pi, if I go underneath and in the anti-clockwise direction, will be the angle that we make when we go all the way around from the positive real axis underneath until we get to the negative real axis. So my angle is not that far, so it will be between and within my domain. So I'm going to try and find this theta, and this will be the principal argument. You can do this in multiple ways using a lot of knowledge about trig and triangles. I'm going to show you the way that I do it, but other people do it differently. So I'm going to draw in a little triangle where my complex number is. And notice that theta would be negative pi, okay? but then we're going to go and plus on this little alpha angle here. Now I can find alpha by using my knowledge of tan. So let's draw in this triangle, and I'm just going to omit any negative signs. Just leave it as positive, that's okay. So I have opposite is 3, adjacent is 3. So tan alpha is 3/3, or tan alpha is 1. And I know that my alpha is acute. Now there's only one acute angle here that I know for which tan equals 1, and that's pi on 4. If I do that, then I get theta is minus 3 pi on 4. And notice this is within my domain. It's bigger than minus pi, but smaller than pi. So the principal argument is indeed minus 3 pi on 4. B and C will do the same process. B is rather nice, and C is a little more complicated, as always the case with complex numbers. It will be Z2 or minus 7. I'm going to rewrite that as minus 7 plus 0i. The graph of this. This will tell you everything. That's why I say always graph it. Okay, I know this complex number has no imaginary part. It's just 7 units in the negative direction along my real axis. So the angle that it makes with this real axis, well, either I could start at the positive real axis and go anti-clockwise up and over. And we know what this angle is in radians. This would just be pi. And that is within my domain. So I'm going to probably use this angle. Notice if I decided, okay, let's try going the other way. Notice that this angle here all the way around would be minus pi. But I can't have minus pi included here. Okay? So for that reason, our argument of minus 7 plus 0i is just theta equals pi. See, similar process, but just notice that we will need to rationalize our denominator. So multiply the bottom and the top by 1 minus root 3i and see what you get. This will allow us to sketch the graph better. On the numerator, we'll get minus 2 plus 2 root 3i. And on the denominator, we'll have 1 minus 3i squared. But recall that that I squared is really just a negative 1. So on the denominator, we'll be left with 4. Again, you can simplify here if you take a 2 out the front. So you should get something like minus 1 plus root 3i all over 2. I'm just going to rewrite mine at the top here. If we break it down, we'll have my real part as minus a half. My imaginary part will be root 3 over 2. Okay, I can sketch this now. Before, I really had no idea what that looked like. Let's go minus a half in the left, and then root 3 over 2 up in the imaginary. Here's Z3. Okay, first step, always look, do you have to go around clockwise to get to your Z3, or do you go around anti-clockwise to get to your Z3? If I go clockwise up and around, I know that this theta is definitely less than pi, and it's definitely greater than minus pi. So it is within my domain. Again, if I just check just for fun, if I went around the other way, notice that I'm going to get outside my domain because I'm going negative pi and then a little bit more negative. So it's going to be too negative to fit within my domain. That means we're going to go anti-clockwise around. Again, I'm just going to draw a triangle to figure out what my alpha is. And then I could say that theta is pi minus this alpha. I'm just going to draw the triangle. Again, I can omit the sides or the signs of the sides. And then I can use my knowledge of tan or this identity triangle to figure out what alpha is. I know this is already an identity triangle. Opposite the root 3 on 2 should be the angle pi on 3 if you remember that. So in conclusion, I have that my theta equals pi minus pi on 3, and that will give me theta equals 2 pi on 3. Again, this is within my domain, but that you can use trig in different ways to find your angle theta. I'm just showing you one way. All right, we'll come back for the second part of the video at another time.